Okay everyone, what we're going to talk about today is transformer efficiency. And then probably tomorrow and later in the week we'll look at transformers themselves and the calculations to do with them. Well, first of all we need to just look at a transformer and treat it like a machine. Although it's got no moving parts, it's technically a machine because it has power going in and power coming out. And I've got this little model here, and this is effectively a transformer core. And I can take the top off there, and you can see there that there are very, very thin layers of what we call laminations, and these help to reduce the build-up of eddy currents, which produce a lot of heat in the core when the transformer is in operation. I can slip a couple of windings onto this core. There's one, and there's the other one. So there we have our transformer, the primary and the secondary. These are actually the same number of turns on each one. 10 turns on each. If I turn that round, you should be able to see the windings just inside these formers. I'll put the core back together again. What's happening here is we have an alternating magnetic field on this side is transformed to the other side through this core, goes straight down the middle of this winding, and it generates electricity in the secondary. So if we put electricity in here, we'll get electricity out. Alternating current in, alternating current out. And you can see the other benefit is there's no actual electrical connection between the primary and the secondary. It's purely through this magnetic field. And what we're going to talk about today, because I'll bring this model out again later in the week, we're going to talk about the losses involved in this actual core, and also the losses involved in a winding. And there's another winding here, and this copper winding has resistance, and because it's got resistance, when electricity passes through it, it produces a small amount of heat, and that heat is lost along with the heat that is generated in the core. It's generated through eddy current losses, and it's also lost through hysteresis losses. And what I'd like you to do is have a look at the transformer book, which I've just uploaded for you, and if you could take a look at hysteresis, and that'll explain what that's all about. The same applies with losses to any machine. For example, this electric motor. When electricity is applied to the motor, it gives us mechanical power in kilowatts, but the motor will get hot, and that loss has to be accounted for. The greater the losses in motors and transformers, the more inefficient they are. The lower the losses, the more efficient they become. So let's have a look at efficiency then. We have a machine here. That is our machine. It could be a motor or a transformer. It has power in and it has power out. And we have losses here, which you can call heat. And this applies to any machine really, so not just transformers. The basic formula is efficiency equals power out divided by power in multiplied by 100%. Now this one on the top of the formula is always lower than the input. You always get less power coming out than you get coming into a machine. And this power is usually expressed in kilowatts, particularly in transformers, or kVA. kVA is just another way of looking at kilowatts from your perspective. We don't do AC theory at this level, but if we do AC theory at level 3, then that effectively will cover kVA. But as far as you're concerned, for this level, kilowatts is the same as kVA. And you may see in some of the questions that you'll get talking about kVA in and kVA out. So if I have a transformer here, let's say for example it has 10 kilowatts in and it has 9.5 kilowatts out, then its efficiency equals power out, which is 9.5 divided by 10. You can see there that comes to 0.95 times 100 equals 95%. Another example would be if I have a transformer or a machine or a motor, doesn't matter what it is. If I say the power in is say 15 kilowatts and the output power is say let's say the losses are 450 watts going off in heat, then if they're the losses, I know that the output power is going to be 15,000 take away 450 equals 14.55 kilowatts. So the efficiency then is 14.55 divided by 15 times 100%. I'll just do that, 14.55 divided by 15 equals 97%. Now motors generally will operate at around about 70 to 80% efficiency. Transformers tend to be very efficient because there are no friction losses in a transformer as such, no mechanical losses, and they can be around about the 90 to 95% efficiency mark. Okay, I'll just have a go over that page again clearly so you can see everything. I'll upload that video, and if you could have a go at some of the questions in Solar, I'll have a look at them tomorrow. Thanks.